Okay, these are a whole collection of practice problems having to do with rotation kinds of ideas. We would have normally done these in lab just as extra practice because you need a lot of practice with all the ideas in rotation to really be comfortable with it. Some of these are old exam problems, some I clearly photocopied out of another book. So let's just go through them in order and look through what solutions I gave are. Problem 1, we've got a 4 centimeter radius grinding wheel switched off at time t equals 0, slows to a stop with constant angular deceleration, and we're given the magnitude of the angular deceleration. And so in this case, that's if it's constant deceleration, that's a constant angular acceleration case. We can use kinematics here. So find the angular speed of the wheel at time t equals 0. Find the initial speed of a point on the edge of the wheel and how many revolutions does the wheel complete on the way to stopping. So let's go down to the solution to problem 1. Find the angular speed of the wheel at time t equals 0. So we can we know it goes to rest with a certain angular acceleration in a certain time, so we can use our constant kinematics equation. Omega final equals omega initial plus alpha times t. That's shown right here. Omega final is 0, it's coming to rest, and it does that in 11 seconds. We're given alpha. In this case, if we're going to take the direction it's rotating to be positive, alpha should be a negative quantity because it's slowing down in the positive direction. And we can solve for the initial angular speed of the wheel in radians per second. Find the initial speed of a point on the edge of the wheel. There we can just use v equals r omega for the relationship between linear speed and angular speed, and the relevant r is the radius of the wheel. In this case, 4 centimeter radius. So I put that, oh, this is a typo. That I converted to meters there, so that should say meters instead of centimeters there. But looks like I'm doing the right calculation there, so that's 3 meters per second. See, how many revolutions does it go through on the way to stopping? Well, that's a constant alpha kinematics kind of problem. We want to find delta theta, so we can either use, theta versus t. We know the t it took, so that's the way I chose on here. Theta minus theta 0, that's delta theta, is equal to omega 0 t. We now know what omega 0 is. And 1/2 alpha t squared, remembering alpha is negative, and we know the t is 11 seconds, so we can calculate it that way. You could also use omega final squared equals omega initial squared plus 2 times alpha times delta theta and solve for delta theta. That way we know all the information that goes in there too. 2. A meter stick is pivoted to rotate without friction in a vertical plane about the point labeled axis. So here it is. It is raised to the configuration shown by this dashed line there and released from rest. And it falls, of course, so it's zooming by the bottom sometime later. The plus y direction is upward, away from Earth's center, plus z is out of the page. Call counterclockwise rotation direction positive for angular quantities. Okay, counterclockwise is positive, so it's going to be rotating, at least in this initial part of the problem, in the clockwise direction. That's a negative rotation direction. Okay, provide answers to the following questions. Circle the best answer. 0 means the magnitude of the quantity at that instant is 0. When the meter stick first reaches its lowest position, what is the torque on the rod about the axis due to gravity? So when it first reaches its lower position, that's the solid picture right here, what is the torque on the rod about the axis due to gravity? And the idea is it's 0. Remember, one way to think about it is, at this instant in time, we can pretend the gravitational torque, as always, is all concentrated due to a force at the center of mass. So there would be an arrow going down in this direction. And the moment arm for that force relative to this axis of rotation is 0, right? To find the moment arm, we draw the line that contains the force, and look at the shortest perpendicular distance to the axis, and that line goes right through the axis, so the moment arm is 0. So gravitational torque is 0. Angular velocity of the rod about the axis is positive, negative, or 0. Remember, we're saying rotations in the counterclockwise direction are positive. In this case, it's rotating in the clockwise direction at the instant shown, so that would be a negative angular velocity by that convention. The angular acceleration of the rod, in this case, we can use torque net equals I alpha. We already found there's no gravitational torque. No other forces are trying to twist it one way or the other, so the net torque is 0 at the instant shown right there, and therefore the left-hand side is 0. I is non-zero, so alpha has to be 0. The direction of the linear velocity of point A on the rod. So point A is up here on the short stubby end of the rod relative to the axis, and at this instant it's shown it's as this thing rotates around like that, A is moving to the right. That's in the plus x direction. That's what's shown there. The direction of the linear acceleration of point A, in this case, let's see. We already said alpha is 0 here, so the tangential acceleration, because A tangential is R alpha, tangential component of the acceleration of A is 0, but the radial component of the acceleration is non-zero. It's going to be pointing towards the center of rotation, so that's down for A. Down is in the minus y direction, so the total acceleration, since the tangential is 0, we only need the radial acceleration component, and that's in the minus y direction. B, a little while later, the meter stick has passed its lowest point, and it's heading upwards on this side. Okay? The torque on the rod about the axis due to gravity, well, let's see. Gravity wants to try to twist it in this direction, right? Gravity wants it to move down, and that's a torque in the positive direction, right? Because we said counterclockwise is positive, so that's a positive torque due to gravity. The angular velocity of the rod about the axis, well, the rod's still rotating in this direction. Positive is the opposite direction, so it's a negative angular velocity. Angular acceleration of the rod about the axis, well, let's see. The torque, we already found out, is positive, and therefore from torque net equals I alpha would give a positive alpha, the angular acceleration. So that's why that's positive. And the direction of the linear velocity of point A on the rod, well, at this instant when this end is going up, A is going down, so it looks like it's moving in the minus y direction. Okay, problem 3, we have to go back up to the top to see what that problem is. That's an Atwood's machine, 2 masses, different masses attached on a massless ideal string, which is looped over a frictionless pulley, but the pulley is not massless. It's got significant mass to it. Radius 10 centimeters, mass 2 kilograms for that disc. It rotates without any friction at the axle. Find the magnitude of the linear acceleration of the system. In other words, how fast is this one going to go up, or what rate of acceleration is this one going to go down? So in this case, we've got to do three equations for the equation of motion. We're going to do free body diagram for this one and do F net equals ma here. Free body diagram for this one, F net equals ma here. Remember, we got to take consistent axis directions, since we know this one's going to go up, this one's going to go down. We'll take plus to be up and plus to be down for this one's free body diagram. And then also torque net equals I alpha for the disc. And we'll take the positive rotation direction to be this direction to be consistent with the other ones, right? We write down those 3 equations, and we've got 2 different tensions. So we've got T1, we've got T2 on this side, and we've also got an alpha and an A, and we can always change out the A's for alphas In this case, the acceleration of this one is equal to the radius of the disk times alpha, and the acceleration of this one is the radius of the disk times alpha. So we can replace alpha with a's in those cases. Okay, then I'll get three equations that will involve the variables t1, t2, and alpha. Let's go down and look at the solution down here. Here are my three kind of free body diagrams. This is the equivalent of a free body diagram for torque net equals I alpha. Chosen my consistent axis directions. I wrote down F net equals ma for the first two. I plugged those in to the third equation, torque net equals I alpha, for T1 and T2 that appeared in there. When I do that, I get this on the left-hand side, and for my alpha, I've replaced it in terms of A. Alpha for the wheel is A divided by the radius of the disk. When you substitute those two T1s and T2 expressions into the third equation, you get this big mess, and then I can put all the A stuff on one side, all the non-A stuff on the other side. Amazingly, it reduces down to 9.8 equals 6A, so I can solve for A as 1.63 meters per second squared. That's how fast the two blocks are accelerating linearly. Problem 4. A uniform solid sphere of radius r is placed on the inside of a hemispherical bowl of radius r. Sphere is released from rest. You know, this is actually a really complicated problem, I will say, or at least it's confusing to set up. In this case, we're supposed to determine the angular speed of the sphere when it reaches the bottom of the bowl. So we release it from rest at some angle theta relative to the bottom of the bowl, and the question is, how fast is it rotating about its center as it zooms past the bottom of the bowl? I wouldn't consider this a typical kinds of problem. If for no other reason that you're not given any numbers in here, it's all in terms of symbols, which makes it much more complicated. But we're going to use energy methods, and you use, W net equals delta KE plus delta PE, and for this thing rolling without slipping going to the bottom, take the system to be the rolling sphere plus the earth where gravity is internal, but we'll take the friction and the normal force to be external forces. And then do W net equals delta KE plus delta PE. Okay, here it is. This is from a term where when I was writing the solutions, K is KE and U is PE for the way that Giancarlo writes it. Okay, so we're going to take our system to be the ball plus Earth. The other two forces are external, but they don't do any work as usual. So the left-hand side is 0. The right-hand side for delta KE, we have two terms. We have the 1/2 I omega squared plus 1/2 mv center of mass squared for rolling without slipping. So I need those both in the final state and in the initial state, but in the initial state it was released from rest, so its initial kinetic energy is 0. And then I also, for change in potential energy, I have mg times delta y. Delta y is going to be this small amount at the center of mass goes down. It should come in with a minus sign. You have to do a little bit of geometry there. This distance right here is big R minus little r. This distance right here is big R minus little r, all times the cosine of theta. And therefore, the distance the center of mass falls is big R minus little r minus big R minus little r, all times the cosine of theta. And when you simplify that down, that gets simplified to big R minus little r times 1 minus cosine theta. And remember, it's going down, so delta y is negative. Putting all that mess in here, including the moment of inertia about the center of mass for a solid sphere is 2/5 mr squared. We do get kind of a mess, and also I'm substituting in for V center of mass in the final state is equal to R times omega. That's the relationship between the center of mass speed and the angular velocity about the center. Then I get an equation that only involves omega squared. I can combine together the two omega squared terms and solve for omega. Again, it's sort of a mess because we didn't have any numbers to sort of simplify things as we went along. So don't consider that a typical problem. That is the absolute pinnacle of hardest kinds of problems that we can do with these energy methods. Problem 5. Two skaters, each of mass 60 kilograms, are initially moving in opposite directions with speed of 1.5 meters per second squared. When they pass each other, they are 4 meters apart. They each grab onto ends of a 4-meter long massless pole, and then they start moving in a circle about the center of the pole, and we're going to assume their skates slide without friction as they move in a circle after that. What is the angular velocity of the system consisting of the two spinning skaters, excuse me, as they spin in the configuration shown? Well, the idea is when they start spinning, whatever their speed isn't going to change as they continue moving in the circle. They're just going to transition from moving linearly to moving in a circle at that same speed. So whatever speed they had initially, that's the speed of their point on the edge of the pole as they move in a circle. So we know that final speed. If we want the angular velocity, we can use the relationship between linear and angular velocity, v equals r omega. And that means we know v is 1.5 meters per second. We set that equal to r. It's a 4-meter long pole, so r relative to the rotation axis, which would be at the center afterwards, r is 2 meters for each of these. So 1.5 equals 2 times omega, solve for omega. So it's actually a pretty simple problem there. 6, find the z component of the torque that the force F exerts on point C in the diagram. So here, for some reason, somebody is pulling in this direction at 30 centimeters away from point C, with this angle being 40 degrees. So probably the easiest thing in this case to do is just say, I need to find the perpendicular component of the force. To find the perpendicular component, we would take 100 newtons times sine of 40, and then multiply that times the total distance, which is 0.3 meters. So, in problem 6, 100 newtons times sine of 40 times 0.3 meters. Oh, and I guess I missed the sign. Oh, okay, it looks like here I didn't specify in this problem. So the magnitude of the torque would be this number without the minus sign. If we take counterclockwise to be positive, then we did an extra minus sign in front of it. But I don't think that was in the statement of the problem.